So, in this chapter, we're going to talk about derivations and application of Greek letters. So, the Greek letters are defined as sensitivities of option price to a single unit change in value of either a state or a parameter. Okay, so they represent different dimensions to the risk in an option. Okay, so we say that financial institutions selling their option to their clients manage their risk by Greek letters analysis. Okay. We're gonna have a look firstly as the delta. Okay, so the delta, I'm gonna write that properly. A delta is the rate of change of the option price respected to the rate of change of asset price. So here pi is the option price and S is the asset price. So I'm going to derive the delta for different kinds of stock option. I'll take an example. Black Scholes pricing model for a call option on a non-dividend stock. So I'm going to write it here. And for a put option, is written here. So I'm going to define D1 and D2 for you. Where you have ST being asset price, X being exercise price, sigma being the risk. Where tau is equal to t minus small t, and where the n here is the cumulative density function of a normal distribution. You know that these are cumulative density functions. Alright. Now, what is n of d1? N of d1 this is the cumulative density function of d1. Now I want to introduce it as a normal distribution. Fu for a normal distribution is 1 upon 2 pi e minus u squared over 2 du. The first derivative of d1, okay, is given as this, okay? And since I want the first derivative of this normal distribution here, which is denoted by the equation in the curly bracket, becomes, you just remove the integral. Okay, now the u becomes d1 squared. All right. Oh my gosh, I've just made a mistake here. This is derivative of d1. Similarly, if I want to find the first derivative of d2, it's going to be this. Now, let me introduce d2 is equal to d1 minus sigma. Okay, this is d2. Therefore, my first derivative of the normally distributed d2 would be given as this. So this is an exponential expression which I can break as follows. Okay, you just complete the square here and you break the exponential. Okay. I will replace the D1 I will replace the D1 here. That's gonna be ln st over x plus, just have a look here, r plus sigma square s over 2 t. Alright, so I have this sigma square root 2, which will get cancelled out with a 1 in here. I'm just gonna erase it. Alright, so that would be ln st over x plus r plus so multiply by exponential sigma squared 2 over 2. That is 1 upon root 2 pi e times the ln is just st over x okay, and this will get cancelled out with this. I will be left with exponential r2. The two exponential would just cancel each other. Okay, so we're going to use this formula for deriving Greeks. So I'm just gonna rewrite it in red because this is going to be used throughout the derivation of Greeks. So now I have the first derivative of the normally distributed d2 to be 1 upon root 2 pi exponential of minus d1 over square times st over x times r2. Okay, so now we want to find the derivation for a delta, which is derivative of the call option over st. Okay, so let me just have a look here what I have. Okay, so I want to derive ct over st. I have ct here being st and d1 minus and d2. Alright, now to derive this, how do I derive ct over st? Product differentiation plus this is the derivative of the product, this bit here, minus, because I'm deriving with, differentiating with respect to st. Here, this is a constant, made something here. We missed something here. Plus st, I derive d1. First, I'm going to derive and d1 with respect to d1. And then, since I have to derive it with respect to st. Okay, now I'm going to continue this here. Minus x e power 2, it being a constant. And I first differentiate d2 with respect to d2 and differentiate it with respect to st. Okay, because in the end I have to differentiate with respect to st. So if I just draw a line here, this gets cancelled out, so we will have it differentiated with respect to st. But for convenience, for mathematical convenience, we have to write it as such. Now, let's work it out. I have normal cumulative distribution of d1 plus st stays same. I get the normal derivative of nd1 with respect to d1 here to be 1 upon 2 pi times exponential minus d1 square over 2. Now I have to differentiate d1 with respect to st. Okay, where is d1? d1 is this, so I have to differentiate it with respect to st. This equation here. So what do I get? Let me just write what is d1. d1 is ln st over x plus r sigma square over 2 and I want to find the derivative of d1 with respect to st. So it's going to be 1 upon st sigma s over this. Okay, because of this. ln of st over x is 1 upon st. And I have this. And this is a constant, so its derivative is 0. So that is going to be I'm just going to erase it for space. So minus x. Okay. The derivative of n2 over d2. You get it here. 1 upon root 2 pi and this is same as derivative of d1 over d2, partial derivative. Okay, so we have n d1 okay st. I'm confused right now. So let's see what we have. Okay, I have plus st 1 over 2 pi tau st sigma s d1 square over 2 minus, so this x gets cancelled out, the exponential cancels out, equal to, so you can see that this will cancel each other, which is equal to the normal, cumulative normal of D1. Okay. dct over dst, which is gamma is nd1. Similarly, you should be able to prove that for a put option, it is nd1 minus 1. All right. Second is I'm going to consider delta. So delta of a call option I have stop price and I have call option price. At point A, E dash. So this is the tangent of the line. The slope is the delta. Okay. Okay, now I'm going to explain a delta neutral strategy. You suppose that a financial institution selling option to a client can make a delta neutral position to hedge the risk. Okay, so suppose ST equal to 100, call price is 10, and the delta of a call option is 0.4. A financial institution sold 10 call option to its client so that the client has the right to buy 1,000 shares at maturity. Okay, so just write 1,000 shares at T. To construct a delta hedge position, the financial institution should buy 400 shares of a stock. If the stock goes up to $1, the price will go by $0.4. In this situation, financial institution has $400 gain in its stock and 400 loss in its option position. The total payoff is 0. Okay, let me explain. So ST goes by $1. Option price will go up by $0.4, and if I have bought 1,000 shares, it gives me a gain of $400 in stock position. And 400 loss in option position. So therefore you have the total payoff is 0. On the other hand, if the price goes down by $1, I still have a 0 total payoff because it will make a loss of 400 in stock position. And no, it will make a loss of $400 in stock position and a gain of $400 in option position. So we say that the relationship between option price and stock price is not linear. So it changes over different stock price. If the investor wants to remain his portfolio in delta neutral, he should adjust his hedge ratio periodically. The more frequently adjustment he does, the better delta hedging he gets. Okay, so I'm going to use and show delta hedges here. Okay. Underlying stock is 20. So let me just show you. Portfolio value and stock price. So that's a graph of portfolio value and stock price. When stock price is 20, the investor will use only delta as a risk measure, considering that portfolio has no risk. Okay, if it goes to 18 or 21, we'll have to use different delta hedging. So I'm going to stop this video here and make another one in the next section.